Welcome to the first talk of 2019 seminar series on modern artificial intelligence at the NYU Tandon School of Engineering. This series, which we launched last year, aims to bring together faculty, students, and researchers to discuss the most important trends in the world of AI. And this year's speakers, like last year's, are world-renowned experts whose research is making an immense impact on the development of new machine learning techniques and technologies. In the process, they are helping to build a better, smarter, more connected world, and we are proud to have them here. By the way, the talks are live-streamed and viewed around the globe, helping to spread the word about the amazing work going on in the AI community. I would like to thank Dean Jelena Kovacevic, as well as my own Department of Electrical and Computer Engineering, for supporting this series and graciously hosting our esteemed speakers. As many of you may already know, Dean Kovacevic came to us from Carnegie Mellon University in Pittsburgh, and she has that in common with today's speaker, Marshall Hebert, who heads the Robotics Institute at Carnegie Mellon. Just like Brooklyn, Pittsburgh has a storied history that captures the imagination. Many people know it as a steel city because of its status as a hub of industry and steel production. Today, thanks in some part to the efforts of Marshall and his fellow researchers, it has another nickname, Roboborough. Today, more than 60 robotics companies make their home in Allegheny County, many as products of the strong robotics program at CMU. Marshall's own research interests include computer vision and robotics, especially recognition in images and video data, model building and object recognition from 3D data, and perception for mobile robots and for intelligent vehicles. His group has developed approaches for object recognition and scene analysis in images, 3D point clouds, and video sequences. In the area of machine perception for robotics, his group has developed techniques for people detection, tracking, and prediction, and for understanding the environment of ground vehicles from sensor data. He also currently serves as editor-in-chief of the International Journal of Computer Vision. Marshall will be speaking to us today about the formidable research challenges of using computer vision in robotic systems and illustrating his presentation with compelling examples from autonomous air and ground robots. I know none of us can wait to hear him, so without further ado, I'll invite him to the stage.
Thank you. Thank you. Great to be here on this campus. Can you hear me? Yes, obviously you can hear me in the back, right? Okay. All right. I'm going to talk to you a little bit about computer vision and more specifically about the issues that we face in using computer vision in autonomous systems or more generally robotics systems. The story here is that we've seen extremely rapid progress over the past few years in computer vision, fueled in part by progress in machine learning, deep learning, and other developments. However, progress has been much slower in moving those results to autonomous system and robotic system. And what I'd like to discuss is a few of the reasons why that is, and a few of the research areas, if you will, that we need to address to accelerate that connection between the progress in computer vision and autonomous systems. So when I talk of autonomous systems, I mean things like this. This is a video from some work from some years ago of a drone flying through a dense forested area like this. The drone has input only from a single camera and has to generate in real time the steering command, left-right steering command here. This is another example here from another group at CMU, the Robotics Institute. This is 3D mapping of an environment. This is in the context of self-driving, for example, a car driving in a street. You see the speed here, if you do the calculation, that's about 100 kilometers an hour in the street of Pittsburgh. We're not supposed to do that, so unfortunately I'm being streamed, so that's bad, but okay. This is a real application. This is from a group at National Robotics Engineering Center at the Robotics Institute. This is a collaboration with Caterpillar. Those trucks have been in operation for many years now and have driven thousands of miles. Those are fully autonomous. Okay, there's no human interaction here. So this is basically one example of self-driving type of thing. This is a slightly simpler environment than the on-road self-driving because, of course, you don't have other agents and so forth. But that gives you an idea of what we try to do in robotics and in autonomous systems. This is another example. This is from Basti Sher's group and Sanjeev Singh. This is a fully autonomous helicopter. Now you have to deal with, you know, everything from bad sensor data, from complicated dynamics. Okay, if you think of the planning that you need to do, there's no room for error here. And this is kind of the point I'm trying to make with those examples. This is the key difference between, you know, what is called sometimes type 1 AI, the kind of thing that you have in a question-answer system, you know, Siri or Alexa, that kind of thing, where first of all, you can make some mistakes. It's okay. Nobody dies. Okay. You also don't have strict time and computation constraint, unlike the examples that I showed there, where an output needs to be generated within some number of milliseconds, and a decision has to be taken within some number of milliseconds, and you cannot make a mistake. So those are the kind of additional constraints that we have to take into account now when migrating those computer vision techniques to those kind of systems. Okay? Another way to say it is if you see your typical vision paper, you know, and you have 95% performance on whatever data set, or 99%, well, for those systems, 99% is not good enough. You need to do, you need to have basically continuous performance in every single image that you acquire, every single bit of sensor data. So those are the kind of problems that we need to look at to be able to use those techniques effectively. And by the way, if you're interested, there's a couple of sources here, the, you know, some special issues of robotics journals on long-term autonomy and robust autonomy and things like this that analyze in more detail the kind of requirements that we have for those systems. So what I'm going to do is look at some, basically 3 or 4 classes of issues that we need to address in vision to make it work, basically, in those kind of systems. And to do that, I'm going to use this diagram, which is the simplest possible view of an autonomous system, okay? Actually, I have one later that's even simpler with only 2 boxes, but we're going to start with 4 boxes, okay? So you basically have some sensor input. For our discussion, it doesn't really matter if it's images or videos or 3D data. You have some sensor input continuously. You have some perception box here that outputs some form of output, some interpretation of the environment, and from that you want to make a decision. In the example I showed below, previously, it's, for example, planning for the helicopter or for the truck and so forth. Okay. So the first problem that I'm going to look at is this arrow here. The way I've drawn this here, it looks like this perception box is always going to give an answer, right? You get an input, it gives an answer, you make a decision based on this. The problem with that is that this assumes that this perception box is always able to give an answer, that the input is always going to fall within a universe of input that this perception box can actually process. That is a huge assumption, because it assumes that the system is always going to be in conditions that it is being trained for. So the first set of problems that we look at, and I will show you one example of an approach for this, is to ask the question, should we always give an answer? Should the perception system always give an answer? And number one. And number two, can we anticipate when the perception system should not give an answer, or at least that answer is not reliable? So let me, and this comes on the various names, introspection, self-evaluation, failure detection, things like this. In fact, there is an entire new ONR program, URI program, exactly on this topic of introspection and self-evaluation. So this is an important area. So let me illustrate that on one example. This is a typical vision task, semantic segmentation. This is what you would do in self-driving. This is a video from a car and the output interpretation here. Big progress there. Things work pretty well now with this. You now put this on a robot, and then things can go pretty badly. Okay? They can go pretty badly because of poor illumination condition. Things are too close, too far, any number of conditions. And the reason, of course, is that it's impossible to anticipate all the conditions under which the system is going to operate, and it's impossible to anticipate basically all the things that will go wrong. In fact, we did this. We provided our code for semantic segmentation to people from the Army Research Lab, with whom we're with which we were working. And they basically took our code and evaluated on the robot and then produced this 80-page report on everything that went wrong. It's a really humbling experience, you know. And of course, a lot of things go wrong. So what you really want to do is to be able to look at the input and automatically figure out whether I should really use this input or the output of the perception system to make a decision. So a simple analogy, and that's only an analogy, is if you're driving and you're suddenly surrounded by fog, you know instantly that your vision system is impaired, and you know instantly that you cannot make decisions the way you were doing decisions. So you're going to automatically switch to a different mode of driving instantly. So the question is, can we have approaches that allow us to do this automatically from the input? So this is kind of related to a concept of introspection, basically the ability to evaluate the input to a vision algorithm and to assess whether this input is going to yield to enough performance to be able to make decision and have performance of the overall system. So that's what we're trying to do. Now, one way to do this would be to explicitly anticipate those failure cases. Basically, explicitly try to code those conditions on the input that are going to lead to bad performance. But of course, that's not going to work because you cannot, by definition, anticipate all those conditions. The second way of doing this is to learn features from the input that are predictive of performance. Okay? If we can do that, given the input, we can have some prediction of the overall system performance, and we can then decide whether or not we're going to make those decisions. So this is what we do. You basically have a lot of examples of the system in operation, and you try to have a predictor that will take the input and predict the overall performance. And from that, you can decide whether or not to use the input. Well, for example, in my example of the fog, whether or not your visual system is good enough to drive. This is an example, a non-robotic example. This is for a task, a segmentation task, image segmentation task. And what the system here, the train system here predicts is that the images on the left are hard to segment. In other words, your vision algorithm is not going to do very well. And the images on the right are easy to segment. Now, of course, you look at this and you go, well, obviously. Those are harder than those. The important thing is to be able to do this automatically using a systematic approach to be able to do this. This is another example closer to what I showed earlier in the semantic segmentation case, where again, those are hard images, okay? The ones where the performance is going to be low, things are going to go wrong, and good images here. So if we can do this, we can basically anticipate when failures of the vision system are going to occur, and we can make decisions based on this, okay? By the way, this is a very old concept. This goes back to early days of pattern recognition in radars and things like this, where people used, in those days, used a term that is not used anymore very much, but should be, something called the declaration rate. So you're familiar with the detection rate and the false positive rate, if you have a classifier or any type of, system. So that's typically the performance curve, precision recall or ROC curves with the two axes. But you can have a third axis, which is what is called the declaration rate. And the declaration rate means the percentage of time that you're actually going to produce an output, okay? A declaration rate of 100% means that you always use the output. In other words, you always assume that your algorithm performs reasonably. A very low declaration rate means that you're going to reject most of the inputs. Now, of course, the accuracy is very high. Here, you're being very conservative. In fact, your vision system is going to work really well if you never use the output. It's never wrong, okay? And of course, the performance is worse when you use all of the inputs because sometimes it's going to fail catastrophically, okay? So basically, the idea is that if you can do this introspection, meaning this prediction of performance, you can have the third axis, and you can basically set that threshold on this declaration rate axis, Okay, if you're very conservative, you're going to be on this side. If you're willing to take more risk, you're going to be on that side. Okay. So let me give you an example here. This is an example from a drone flying. Okay, this is what I tell myself every morning when I get up. And so basically, what we're trying to do is look at the. So this is an example here of vision system. This is input video. This is monocular, by the way. Input video and output estimated depth map. There is nothing profound about the vision system that is used here. This is pretty standard. This is another view here of the system in action. So this is the input video here, the estimated depth map, and this is a 3D view of the same thing. The way this works is that it constructs this 3D representation, local 3D representation of the environment, and evaluates trajectories to fly through. Now, the problem, of course, is that if the vision goes bad here, if this estimate of the 3D environment is bad, then we can have a catastrophic failure of this estimating the trajectory and catastrophic failure of the system. So what we do is to take that input video, learn from training data how to predict performance from the input data, and use that predicted performance to decide whether or not we're going to use that input. Okay, a little bit like in my Ford example, if I sense that my vision system is impaired, I'm going to slow down, I'm going to do something different. That's basically the idea, anticipating failures of the vision system. It's not too important how this is learned. This is using some neural networks as usual to do this. The important thing is that we can learn this directly. Now, there is a question of how do you train such a system, right? And the way this is trained in this case is to have ground truth of the 3D environment. This is done as a detail using stereo cameras on the drone at training time. Since we have ground truth, we know which trajectories are clear and which are obstructed. So we have ground truth on the trajectory. And we can then measure the performance of the system, meaning compare the actual trajectory distribution with the one that I get from by using my vision system. Okay? If it's the same, then it's good performance. If it's not the same, or it's very different, then it's bad performance. Okay? That's the ground truth, if you will, for the training system. And from that, we can learn how to do this prediction. Okay. So we can look at how well we predict those failures of the system, and we can then plot basically this detection rate. We can plot as an ROC curve how well we detect those failures. And this is the example here. False positive rate and true positive rate on detecting those failures. The red here, the red curve here is what would happen if we were to use just the confidence on the vision system itself. Okay? Any vision system is going to give you a confidence, an internal confidence on its own output, and you could use that to do this prediction. But it turns out we do much better by doing this introspection, which is not surprising because the confidence of the vision system relies on the fact that the input is a variable input. So we can learn a better representation, if you will, of the performance prediction. Let me show you this example here. Let's see if this video, yeah, this is going to work here. So this is again the example of the thing flying here. What you have on the right is a scale that's going to show how confident it is in the output. When the scale is high, it means high probability of failures, which is what happened right here. What it does at that point is to enter a different mode of flying. It basically stops and look around until it gets enough data to have enough confidence now on its output. Okay? So this is implemented that behavior that I was saying earlier to detect when the system itself, through self-introspection, when the system itself is going or may fail because of the type of input. If we measure the performance, I don't know what this thing here is, but okay. If we measure the performance by seeing how far we can fly without manual intervention, the green bar here indicate the flying with introspection, in other words, having this failure detection and being able to recover from it. And the red bar here indicate without the introspection. And not surprisingly, we find that can go much further and have a much more robust execution. We can look at what it found. If you go back and see what failures it detects the things that some of the things that you would expect, things like illumination issues, things like rotational motion, which in this case affects the quality of the 3D reconstruction, etc. So, of course, some of those things are not surprising. Those are the kind of failure modes that you would expect. The important thing is that it's able to learn how to detect those things automatically using a unified procedure to do this. All right, let me skip those things. This is another example here of the same thing. This shows only the depth map here. So here we have basically good performance of the vision system. And you're going to see a case here where things get very, very sparse here. And you have a high probability of failure of the system. And it's going to enter, again, a recovery mode, looking around until it gets, again, good data, and then flies again. Okay? So that's basically the idea of introspection. Yes?
If you have, for instance, a fixed-wing aircraft, where you can't slow it down,
yeah.
You have to fly through.
Yeah.
What do you...
Yeah, so let's be very careful here. Here, what I'm talking about is ideas on how to deal with those failures of the vision system. What I have not addressed is what do you do with that information? What strategy do you use once you have that information? And so I don't have an answer to that. That part is still very specific to the system at hand. Okay.
And what sort of error rates? I mean, it definitely improves the error rate. What sort of error rate should we be getting by implementing this on top of the existing vision system? For instance, on aircraft, the 1/10 to the -9 error rate. So what would this get us to?
So again, I don't have the answer in this context, but in the case of the drone, we basically were able, so for example, in those experiments, to reduce the error rate by a factor of 10 or something like that. Right? It's very different. It's very dependent, of course, on the system that goes around it and the way that's used. It's more looking at the principle of being able to learn to characterize the performance automatically. So one important thing that I mentioned in presenting this is how it is trained. And I mentioned this idea of measuring, which trajectories are correct and incorrect and all this, meaning that it's trained on the behavior of the overall system. It's not trained on the output of the vision system. And that brings up an important point, which is a basic problem that I think is pretty much still open, which is the choice of the right error metric or loss function that we use in building those vision systems. So let me illustrate this on this example. This is an example here from a semantic labeling task. So you have an image and you label pixels according to different types of regions. Those are two different outputs, and it's clear to everybody that the output on the top is better than the output on the bottom because there's that big green mistake here that's mislabeled. But if you think about it, why do we say that it's better? We say that it's better because the error metric, the loss function, if you will, that we use, is the percentage of pixels mislabeled. Right? When we train such a task, we try to maximize the number of correctly labeled pixels. And in fact, the objective here implicitly is to label every pixel correctly. The problem with that is that from a robotic or autonomy point of view, there is really no application where you need to label every pixel correctly. It just doesn't exist. Okay? Similarly, when you think of the flying application that I showed earlier, you could measure the performance of the system by looking at the accuracy of the 3D representation. But there again, you don't care if the point cloud is 5 millimeter accurate or 2 millimeter accurate. The only thing you care about is that your trajectories are correctly evaluated. That's it. That's the only thing you care about. So the basic problem is that in many cases, we are using the wrong error metric or objective function in the vision box that we have as part of the system. For example, number of pixels labeled or accuracy of a 3D point cloud. And we're using one that is actually harder than the actual task that we're trying to solve. Right? If I try to label every pixel correctly, I'm actually solving a task that is harder than what I need to, the only thing I need to solve the robotic task. So this is a basic issue that we have in trying to implement those things and in trying to really use vision effectively in those tasks. So in some cases, it is possible. So I showed an example here in flying. There are many other examples in manipulation, for example, where there the right objective function, if you will, is whether I've grasped an object or not, for example. So that's a well-defined objective function. I can label things. I can measure things that way. But if you look at more complex tasks, like this task on semantic navigation, for example, how do you characterize an end-to-end metric for this task? So that's a major challenge, and that's the idea of being able to use the right error metric. Okay, so that was the idea of introspection and understanding the performance of the system. Let me look at a second problem, which is the problem of limited supervision. And the idea here is this. If you look again at my little system here, the data that is used, so this perception box has to be trained from somewhere, from some data. And so the addition to this is that we have lots of data here that we're going to use for training this perception box. The problem, of course, is that that data is generally supervised data, labeled data. It also has to be very large data. This is a major limitation in being able to use those systems, simply because in the kind of online applications that I showed earlier, we don't have the luxury of being able to acquire a very large amount of annotated supervised data. We also don't have the luxury of having time and computation to retrain every time we want to introduce a new concept, every time we change the operating condition. So the second area that we look at is this idea of reducing supervision, okay? And being able to learn those visual models with as little data as possible, okay? So again, the idea currently is that we train those visual models using a very large amount of labeled data. What we want to do is to be able to do this from very few examples, or maybe even just one example, okay? And the reason why that should be possible, of course, is that even though we have only one example here, we might have a lot of experience offline with many training examples and many different visual tasks. So the idea here is to be able to design those vision systems so that instead of just being trained from one label set of data, to use the prior experience to be able to learn those models, okay? So imagine that you have trained your system for many different tasks offline. You now have a new task, say a new class that you want to deal with, a new type of object or something. You want to use all that prior experience to be able to train quickly on that new task with very few examples, okay? And if we can do that, we can reduce the amount of supervision that is needed and have more practical system. Now this falls on the various heading, meta-learning, learning to learn, things like this, which basically means, again, trying to use the prior experience, having learned many models, to now learn quickly on a new model. So let me tell you some of the things that we've been looking at in this space. And I'll talk a little bit about one aspect of that, which I call model dynamics, which is the idea of not just reasoning in feature space or in image space, as is often the case in learning, but in the model space. So let me explain what I mean here. Let's say that we have some kind of classification task, simple image classification task, okay? Let's say, living rooms images versus non-living room images, which is from one of those data sets. So one way to think about it in data space is to think of that as each image corresponding to some feature in some very high dimensional space, maybe. And those features are constrained to be on some subset of that feature space that might look like something like that. And then we have the other class here, which is also features in that feature space, in that data space somewhere else. And the classification problem can be visualized as learning some kind of boundary between the two. Right? There's nothing new here. This is basically what one does in a machine learning setting typically. Now, the dual way of thinking about this is like this. You can think of this task, classifying living room versus non-living room, as generating some kind of classifier, which I illustrate by this blue scribble here. And this classifier is basically a big vector, you can think of it as living in a high dimensional space as well. And it's also constrained because, visual tasks have a certain structure. Those classifiers are implicitly constrained to be on some subset of that high dimensional space. And if you take another task, say classifying another type of class, then you have another model that's somewhere else in that high dimensional space. Okay? So the idea here is to understand the relationship between those models with the idea that if I have trained many models like this is my past experience, then I can have an idea of the structure of that space of models. And given a new task, maybe I can use that knowledge to learn quickly on that new task. Okay? So that's basically the idea. Okay? So let me show you an example here of using that idea. Yeah. Or it can be, it doesn't have to be similar. It can be, yeah. In fact, it's better if it's not, because if you have lots of those tasks, conceptually, now this is, I'm not saying anything mathematical here, okay? Conceptually, you're sampling that set of tasks, right? So it's the dual idea of sampling the feature space, so you have a dense sampling. Instead of that, you sample in model space. Right? So let me give you an example of what we can do with this kind of idea. Suppose that I train a classifier for this category, dog, with only one example. So with only one example, I'm going to get a classifier. For some reason on the screen, this is very dark. There's a classifier, a line here, okay? So I illustrate this classifier by a line here, and it's not going to be a very good one, right? Because you have only one example that you use to do this. Then if you put more example, your classifier is going to be a little bit better. And then with more example, it's going to be better and better. Okay? It's a little bit hard to see. I'm sorry about this, but it's right here. It's moving closer this way to the boundary, okay? And so forth. Okay? Until you have really a lot of example, and now you have the final, what you would call the best classifier. Let's call it that, okay? All right? So the question now is, could you somehow say something about how we went from that guy to this guy? Basically, some kind of transformation here that goes from this classifier, the small sample classifier, to the large sample classifier, okay? And the idea is, if you have enough examples of this kind of situation, in other words, enough examples where you have the classifier for one sample and the classifier with lots of samples, which is somewhere else, then maybe you can learn how to figure out the transformation between the two, okay? So that's basically the idea, right? To essentially regress what the classifier would have been with the large sample from the one that it is from the small sample. Now, the idea behind this, of course, is that there would be no reason for such a thing to be useful or to exist, except for the fact that the underlying assumption is that the visual world is in fact highly constrained, and the corresponding classifier, the corresponding models are also highly constrained. They don't change in completely arbitrary way, and that's basically the idea here. So how this is done in practice? This is done using a network that takes as input the model learned with few examples and produces as output the model that would have been learned with a lot of examples. Okay? And of course, it should have the behavior that the network is simpler if you have more examples, right? In fact, if you have a lot of examples, the network should do nothing. It should be the identity. And as you have fewer and fewer examples, you're going to need a deeper and deeper network to generate that regression. Okay. So that's kind of the idea of what we look at here. Now, the interesting thing about this is that this allows us to implement something that is should be a very natural behavior in learning those things. Imagine that you have a lot of a domain, basically, of tasks in some region of that space. So you have lots of categories. In this example, there's 400 from one of those data sets. Let's say you have 400 categories. And some of those categories are going to have lots of examples, right? Some of those categories are going to have very few examples. Okay? This is basically those categories, 400, ordered based on the number of examples in each category. So this is what happens in real life, right? In real life, you're going to have a few things that are very common and it's very easy to find examples for training, and then many things that are very rare with very few examples. So the behavior that you would like to see happen is to use those categories here to help train on these categories. Right? Basically, to use the stuff that you can get data on very easily to help train on the stuff for which you have very little data. So that's basically what we can do there, because we can learn this transformation using the stuff for which we have lots of examples, and then use it on the stuff for which we have very few examples. And this is a view of what happens here. So again, I have my 400 categories. You can think of that as 400 classification tasks, and they are ordered according to the number of examples in the category. On the left, with the most example on the left, and few example on the right. In fact, on the right, extreme right, those categories have only one example. What the red bar here show are the increase in performance that we get by using this technique. Basically, by training this transformation using the categories with lots of examples to predict that transformation. And you see that it has the desired behavior, which is that it doesn't change anything for those common categories. We already have a lot of data. It doesn't do anything. And then it increased the performance dramatically on those that have very few examples. So this implements this natural idea, again, to have the stuff that's easy helping the stuff that is hard. Okay. All right. So that's one idea. Another idea that we've worked on very recently, this past year, is the idea of hallucinating data. Data. And this is now a very common idea now in learning, which is the idea of using our initial training data to create new data, basically hallucinate new data, so that we can train a better model. So this is just a quick view of the idea here. Let's say that, again, you have your training data with very few examples, because you don't have the luxury of labeling a lot of examples. What we're going to do is to use those initial examples to pass it through a box here that is going to generate a new example here, okay, a new sample. There's different ways of doing that nowadays. I'm not going to detail that, but it's just going to generate a new sample. And then if we do that enough time, we can augment our training data with those examples. So now we have the real data here, the real example here, and the one that we generate here, the new ones, combine them, and then train the classifier with this combined data. And then the interesting thing is that we can, at training time, we can adjust the parameter, basically train the thing so that the system basically learns how to generate those examples so that it best benefits the training. Okay, so that's basically the idea here. So this combines two ideas. The first one was this idea of regressing from source sample. The second one is the idea of generating new data to help in the training. And we see major improvement. The orange bar and the yellow bar are our technique compared to two state-of-the-art techniques in this area on some classification tasks. I mentioned all of this in the context of classification, which is not that useful in practical applications. So we can do the same thing for detection. This is actually new results that are not published yet, but those are results on a standard ImageNet type of task, where the horizontal axis is the number of training examples, starting with one example, so that's one-shot learning. The red line here indicate the techniques that I just described, and the black line indicate reference technique, YOLO, faster CNN, etc. The important thing here is that for very few examples here, we get very low performance here. Here we get higher performance to the level where we can basically bootstrap the training and be able to do things that are semi-supervised and other techniques. Okay. This. Okay, the last thing that I want to talk about, because I have to be careful about the time, is one key aspect of the kind of robotic system that we saw, which is the time aspect. Okay? And to explain that, let me go back to my basic diagram here. The way it's drawn here is the standard way of building those things where I have input. I'm going to compute for a while here, and then I'm going to get an output. And the way it's drawn here, I have to wait until this is done, whatever time it takes, to be able to use this output. The problem is, if you that helicopter or that car or whatever of the system, you may not have the luxury to wait that long. Maybe you need an answer right now. Okay? And in fact, maybe there is a situation where, for whatever reason, you have even less resources and even less time, and now you need an answer, right now. Maybe you don't even care if the answer is not quite the best you could get, but you need some indication right now. Okay? If you think of a very simple obstacle detection, for a mobile robot, right? Maybe because of the limited computational budget I have, I need an answer right now to be able to plan my motion. I don't care if I have the precise location of this thing. If I know that there's maybe something on the right and nothing on the left, that's good enough. But I need that information now. Okay. So that means that we need to think of the perception system in a different way. We need to think of, instead of thinking of a perception module as something that takes an input, produces an output, whatever time it takes, we need to think of the perception system as being able to produce some usable output, no matter what computational budget there is, right? And no matter what time the overall systems need that answer. Okay? So that means we need basically a perception system that gives us an output at any time. And in fact, that's a technical term in computer science. There's a concept, in fact, I have a reference here from 96. There is a concept in computer science of anytime algorithm. An anytime algorithm is an algorithm such that if you interrupt the execution at any time, you get the best possible result that you could get within that time. So for example, if you want to invert a matrix, instead of implementing the algorithm so that you have to wait until the entire matrix invert is computed, you can design the algorithm such that if you interrupt at any time, you get the best approximation of the inverse of that matrix that you could get within that time. Okay? Now that's a different way of thinking about how to design those algorithms. So there's more formal definition of this. This is a reference here from a paper in 96 that define more formally what that means. You want the algorithm to be interruptible, meaning that it can give an answer at any time. you want monotonicity, meaning that the answers do not get worse over time. That's the minimal that you want, okay? You want basically to have better and better answer, better and better interpretation of the environment over time. And the third one is a diminishing return. In other words, that this is important actually because you need to know how long you wait. So you want the answer to improve less and less over time, basically diminishing return. Okay? If we can do that, then we can have systems that are anytime and implement this idea of being able to provide an answer that is usable for reasoning and decision making, no matter what computational budget is. So let me give you just a quick, so this is an example here in terms of semantic segmentation. What in an ideal world, what you would like is to have, if you have very little time, your interpretation of the scene maybe looks something like this, very coarse interpretation. If you have a lot more time, it's going to look like that. That's the basic idea here. Okay, so let me show you some of the things that we've been doing in that space, just to give you the rough idea of what we're trying to do here. So one way to look at that is using, again, a neural network kind of architecture. This is a completely, kind of high-level, idealized view of the system here. You have different layers, different levels in that network. The typical approach would look at the last level, the output at the last level, and try to optimize with respect to a loss from the last level. Instead of that, we can generate, or in addition to that, we can generate intermediate losses at different levels of this architecture, and then try to optimize all of those losses together. So that if I look at the system, or if I interrupt the system at any stage here, I will get a sensible output or useful output. Okay? Now the problem is how to optimize those things together. So one way to do that is to take all those losses and combine them, for example, in a linear combination, and train the system instead of using the loss on the last layer on the output to use this combined loss. Okay? With the idea, again, that if we do that, we're not just trying to get the best possible output in the end, we're also trying to get sensible outputs at intermediate stages in the network. The key challenge here, the key difficulty is how to choose those weights. And there's been, of course, prior work on this. The simple thing that could be done is to use constant weights, and there's prior work on doing this. You could think of using linear weights, also work from 2 years ago on doing this. It turns out that we can show there's some theoretical result that we have on this, as well as empirical result that I'm going to show, that a good way of choosing those weights is to adjust dynamically such that the weight is inversely proportional to the loss at that layer. Another way to say that is that we're going to get more weight to the layers that have a lower loss. Okay? And it turns out that you get a good behavior of the system in that way. Okay, so again, basic idea, the main point here is this basic idea of anytime prediction as an important component of those systems, being able to make decisions with arbitrary budgeted resources. The second point here is this kind of structure, we're weighting structure with this strategy to set the weights. Yeah. So that depends a little bit on the application, but for the let's say in a semantic segmentation, that would be at those intermediate level, you can reconstruct an output labeling, and you compute the error on that output labeling. Now, it has to be adapted a little bit on each application, depending on the actual format of the output. But in most cases, you can do that. Okay? So this is an example here on a classification task. Okay? so on the classification test, it's even easier, right? Because you can just have a direct output. So here, this is what this shows. The vertical axis shows the loss of performance at each of those levels. Right? So building blocks means those levels from 1 to 14 in this particular example. Okay? Loss of performance means that if it's in an ideal world, it should be 0. In other words, I should get at each level the best possible performance that I can possibly get with that number of levels. That's the grid. That's the reference here, 0. Okay, that's the best I can possibly do. Okay, this is what you get with the constant weight, and with the constant weight, you have this really annoying thing that you're pretty close here to the optimal, except for the final output, meaning that you can interrupt here and get some sensible output, except that the overall performance of the network goes down dramatically, which is not what you want. You still want, of course, the final output to be correct. This is using other strategy here, and the red one is using the strategy that I showed. Right? The behavior that you want is you want this red line to be as close as possible to 0, so you don't lose performance. Of course, it's never going to be at 0. That's impossible. Right? 0 means it's an oracle where we've trained the system completely with 2 layers, with 4 layers, and so forth. Offline. Okay? So you cannot reach that. You want to be as close as possible, and you want to maintain the final performance here. So basically, you want something flat that's close here. So that shows you the behavior there. Okay? We've used this with the various classification tasks, and again for segmentation tasks. Let me so to answer your earlier question, this is how it looks like for semantic segmentation, right? You get intermediate results that are refined as you go further in the network, right? So hopefully that implements the kind of thing I was saying. If you interrupt at any time, you have a coarse output, right? Which is a higher error, but is still a usable output if you need to make that decision quickly. Let me skip some of the details here. Spirit of this. So this shows basically kind of the evolution of the output throughout the network, going from a coarse, noisy output to the final refined output. Okay. All right. Okay. So what I showed is some ideas on doing introspection or input filtering, basically having the vision system being to understand its own performance and be able to adjust its behavior. I talked a little bit about this problem of being able to design the error metric or the objective function such that it is tuned to the overall task. One thing I did not talk about is the idea of multiple hypothesis, which is the idea of instead of generating a single output from the vision system, a single interpretation, for example, a single semantic labeling of the scene, to generate multiple hypotheses. I didn't have time to talk about that, but this is also an important thing, because if you don't do that, you assume basically that whatever interpretation is generated by the vision system is basically the only one that you can reason on, and you cannot go back in the reasoning chain. I talked about the anytime prediction and this idea of small sample training, so small sample learning to reduce the amount of supervision. So those are a few of the topics that we look at in vision in the context of robotics and autonomy. And I think I should stop here because it's right about on time. Thank you.
Thanks for the presentation. I have a question about the anytime prediction.
Yeah.
So as I understand, basically you want at every stage the L1s or the Li's should be reasonable prediction. But the way you optimize the loss, basically the weighting, if the loss is not good, this weight goes down. So isn't that loss basically not motivating that the individual stages are good?
So there is an important, it's counterintuitive basically. You would expect the weighting to be the other way around, right? The reason why it is that way is that if the loss is very small, right? So suppose there's one level that works very well. Okay, the loss is very small. If you're not careful, because the loss is very small, if you give it a very low weight, then it's going to, in a way, get neglected in the later stage of training. And what's going to happen is that this loss is going to go up again. You see what I mean? So you need to make sure that if a level is as a low loss, is at a good level of training, that you heighten the weight so that it gets preserved, if you will. That's the logic, the intuition, if you will, behind this. Right? Yeah.
And there's a bit of a discussion in the field whether, we should rather invest more time and resources to develop end-to-end learning systems, or whether the autonomous systems it's better to keep them modular. And one of the key, arguments behind modular is that, you can control each part of the system. It's more interpretable potentially. So what would be your take on
Well,
that?
yeah, so I'm not sure, because as I say, it's still an open problem. But in the introspection part, the interesting thing that's going on there is that the system is designed in a modular fashion, right? In other words, the vision system is trained separately and designed separately, like you said. But this performance prediction part is end-to-end. So you could actually have both, right? Where you have the system trained in a modular fashion, but then it's performance prediction and performance control and overall control of the system being done end-to-end. Okay, and I think that's. I think from what we've done, that's a good compromise, because training fully end-to-end, the problem there is, of course, you completely lose control on what the system does, or any explainability at all of the system. All right, doing it purely modular, then you have the problem that I explained, right? That you have mismatch between the individual module and the overall task. So doing it modular and then having the overall performance characterizable and predictable is the compromise, basically.
Let's thank the speaker again, please.